And we are live. Yo, Flows, what's up? Good to see you all. Thank you for coming. Glad you could make it. This is the part 2 of Lou discussion. We got Lou in, we got Jeff Congal, and Ryan S. How you guys doing?
Good.
Doing good.
I'm
Glad you
good
guys
too.
could make it. It's good to see you. Before we do start, though, I have a few shout outs to make. First of all, I have to shout out Vicky. It's her birthday today. So happy birthday, Vicky. I hope you were spoiled rotten, and I hope you're going to be spoiled rotten for the rest of the evening. And
Happy birthday.
happy birthday
Happy
to you.
birthday to you.
And then I want to give a shout out to Triple X for sending me a $10 PayPal. Really appreciate your support, man. You rock. Thank you very much. And then a huge shout out also to Mr. Jeff Conkle, who's literally sourced the part that I've been looking for the generator for a long time in Canada and sending it to me. All free of charge. No idea why you're doing this, but I don't know what I'm going to do to say thank you.
I think I know.
Why is
So,
that?
Because
You know
you
why?
because you want to. Because you want
I'll have
to.
to do.
Yeah.
I'll have to do OnlyFans for him.
What?
I'm just joking.
I mean, why else would you do it, right? Unless you wanted to.
I am doing it out of the goodness of my heart.
Yeah.
Because I enjoy this channel and that's just the way me,
Yeah.
right? Just me
Well, I
being me.
really-
That's pretty much one of the reasons I did the super chat too.
Well, I really appreciate you guys' support. Yeah, Lou, as well. I mean, you know it's flat by heart, Lou.
No, unfortunately,
You're just in
for
denial.
you.
Lou, you're just in
Unfortunately
denial.
for you.
But yeah, thanks again, Jeff. I really appreciate it, man. If there's anything I can do to say thank you,
No worries, it's all good.
just hit me up, man.
Yep.
Really appreciate it. It's really going to help because, I mean, yeah, like I said, since that's happened, I can put the generator on and all it does is just run the Wi-Fi. That's it. Nothing else, which sucks.
Yeah.
You need a new one.
Nah, I just need the coil. And that's what he sourced for me, which is really awesome. I'm just glad you could get it because I can't get it yet. Everything I try, yeah, they say, no, just buy a new generator. So yeah, it's good to see everybody. Thank you all for coming. Really appreciate it. You guys rock. And I guess we want to move on to what's going on. This is where we ended up last time. Behavior of gases. Remember that, Lou?
Yep.
So you say we have to move on to Earth's gravitational field, or do you want us to do behavior of gases again?
Well, let's do behavior of gases again
Behavior of gases.
to refresh.
Okay, guys, please hit the like, share the show. It really does help to have you guys here and help to let everybody know there's a show going on. So appreciate all of you. Okay, behavior of gases. Gases tend to disperse and fill the available volume uniformly due to the random and high-speed motion of their molecules. This principle might suggest that Earth's atmospheric gases should disperse into the vacuum of space. However, the dispersion is counteracted by Earth's gravity. Who's going to break it to Lou?
Gravity does not pull down gases. So, yeah.
Well, gases have matter. So.
What is gravity?
Yeah, that's another thing.
It's an
While you're doing
attraction
that, I'm going to get a video
matter.
quickly. Yeah, gases aren't affected. The direction of gas isn't affected by gravity. This is physics 101, mate.
Nah,
Yeah.
I disagree, unfortunately, for you.
You can disagree all you want, but physics shows it should be true. Let me get a video
Physics
quickly to show you.
the opposite.
No. Just
funny.
quickly get a video to show you. Because if you don't need to believe me, you can probably believe other people saying it, correct?
Yeah. So.
Yeah.
Not flat. That's it.
I see someone else is popping in. PJ Cruikshank in the house. What's up, man?
No, it's all good, all good.
The meeting's just it.
Yeah, just in the meeting with Paul and that. I heard Luch. I missed him singing "Happy Birthday" or something. Did I?
Yeah.
Oh yeah,
happy
Luch. Do
birthday.
you want to sing "Happy Birthday" to Vicky?
Oh, okay, sure, why not? Here again. Happy birthday to you. Happy birthday to you. Happy birthday, dear Vicky.
Happy birthday
to
you.
Hooray! Yeah.
What a sweet voice you got, Luch. That's brilliant, man.
you.
And
That's
many
brilliant.
That
more
wasn't bad
on
at all,
Channel
Luch.
4.
Thank you. Thank you.
Bless you. That was
That
cool.
wasn't bad at all. Yeah. I'm just looking for
Glad I
that video.
did it justice.
You did.
But yeah, I can't seem to find the video. Why not? I really should reword the videos a bit better, maybe. Oh no. I'm looking for where they're talking about gas pressure.
I did put
And,
an analogy.
Oh yeah. You put an analogy, but I'm saying based on what I'm looking for, it's okay. Well, anyway, I'll look for it later. Let's see what you carry on saying. Your analogy is Earth's gravitational field. Is that your analogy?
You can
There we
read
go.
the Earth's gravitational field and the analogy.
Okay.
Yeah.
Earth's gravitational field. Gravity is the force that Earth exerts on all objects. Just have to tell you, sorry, gravity is not a force, so no, it can't exert a force. Pulling them towards its center. This force is what keeps our atmosphere intact. Earth's gravity is strong enough to hold onto the molecules in the atmosphere, especially those closer to the Earth's surface, like nitrogen, oxygen, and water vapor. However, it's less effective at holding onto lighter gases, especially those at the top of atmosphere, where the gravitational pull is weaker. Okay, but like I said, gravity is not a force, so it can't pull anything down. You would agree that even if gravity was a force in your rhetoric, that it would be based upon the amount of mass of a gas? So the more mass it would have, the more attractive force it was if we gave it as a force, but it's not. You agree with that?
The more mass would be more attractive force. Yeah, that's right.
How much mass has the densest gas on Earth got?
Well, density is not really what causes the pull. It's more mass, I think.
Yeah, that's what I'm asking. Yeah, but would you know what mass is?
It's mass is just stuff.
Yeah,
How
density.
In a volume.
It's the amount of matter in a given volume. So it's density.
That's density, right? Yeah.
Yeah.
Density is the amount of stuff compacted into a volume, yeah.
And mass?
And mass is the amount of stuff, I guess. Just a lighter has mass. You know, everything has mass. Gases have mass.
I would agree. Everything has mass because it's practically just substance. Okay.
Yeah.
But now the issue comes in: are you claiming gas has weight?
Gas would have weight, yeah.
How would you know gas has weight?
Scuba tanks weigh
Wouldn't it
more
have-
when they're full of gas.
Wouldn't
Okay,
it have to be static to be able to weigh it?
Scuba tanks weigh more when they're full. You know, of
Yeah, but that's
oxygen.
contained. You have to calculate the weight then, but you can't weigh gas on its own, can you? It's unbonded.
I'd say probably not. No.
Okay,
But
Luch,
gas
do you know what
does have
happens to
weight.
gas when it's compressed?
What happens?
It changes phases. It's no longer a gas. When you're compressing it, it's no longer a gas when you do that, right?
I'd imagine it would be, wouldn't it?
No.
No?
Like okay, for example, propane. Why do they call it liquid propane? It's a gas. How is it liquid? It's because it's compressed.
Butane compressed as liquid. Yeah.
Like, do you know what is liquid propane?
I'm sorry?
Do you know what liquid propane is?
Do I know what liquid propane is?
Yeah.
It's propane gas that's compressed into a liquid. Right?
It's yeah, it would be propane in liquid state, right?
Someone got Skype call.
Yeah, sorry,
It's-
that's
propane in its liquid state, right? I guess.
Okay.
Under pressure, it becomes liquid, right?
Yes.
Hmm.
That's and the thing is now you've changed its phase. It's no longer gas. So you're not measuring the weight of the gas anymore. You're measuring the weight of a liquid.
Yeah.
Okay. So how can you measure the weight of a gas then?
Scuba tanks, you know?
Oh my goodness.
I don't think you're getting it. Let's put it this way. Would you be able to weigh the volumetric mass, the volumetric weight of that scuba tank if the scuba tank wasn't there?
Probably not. No.
Why would that be?
Well, you know, it's all over the place.
Dissipates.
It's dispersed.
Yeah, exactly. So
You need to contain
by
it
proxy,
first.
by default, when you're bringing up a container, as you're putting it, with gas in to weigh it, you are by default conceding then gas requires containment to be able to exist as pressure.
It will. The argument was gas having weight, which it does.
But if it had weight, would you need a closed container?
To be able to measure it properly, yeah. I'd imagine.
So why would you need a closed container if gas had weight being pulled down by gravity, especially if it's claimed to be stronger closer to the Earth?
Yeah.
It's like it's very hard to weigh gas when it's not in a container.
Yeah, because gas requires containment. That's the whole argument.
No.
Yes.
Well, okay. Well, gravity. There you go.
But that's what I'm saying. Gravity is not a force, first of all. And secondly, like we're saying, if you're claiming gravity is the strongest at Earth's surface, why can't it hold gas down on Earth's surface, but you expect it to hold it down when it's further away from the mass?
It did say that. I did write that. Let's see. That the further away is from the surface, the weaker the pull is.
You get what I'm saying? So why would it not being able to... Okay, I found the video. I'm going to quickly show it to you. And I want you to listen quickly what is being said, okay?
Okay.
So the pressurized atmosphere is kept there by gravity, as I said multiple times. So
Hi, I'm Emerald Robinson, and in this What Is video, we're going to investigate the state of matter called a gas. Gases are materials that have no definite volume and no specific shape.
Your whole idea of, oh, Mark has no answer. I do have an answer. Sphere is kept there by gravity.
Third, gases can flow from one area to another. Although the direction of flow is not directly affected by gravity.
Sphere is kept there by gravity.
Although the direction of flow is not directly affected by gravity. Although the direction of flow is not directly affected by gravity.
Did you hear that? What did he say about the direction of flow affected by gravity, Luch?
It's not affected by gravity.
Yeah.
Huh.
Weird.
Mm-hmm.
What's the point there?
Point is, gravity, even if you give it as a force, can't do anything to gases.
The gas, yeah. It can't
affect the
contain it.
direction of gas. What's up, Anthony? How you doing?
Direction is other forces can, other forces
What other
like
forces?
wind and stuff.
Wind
Those
is just gas moving, you know that.
definitely have an impact on the flow of gases.
But wind is gas. Did you know that? Just moving gas.
Well, wind is like what is wind? Do you know what causes
Moving gas.
Yeah, it's just high pressure moving to low pressure, isn't it? Hey, I've just got 2 questions for your guest, if I may.
Yeah,
What's
go ahead.
that?
But can I just quickly shout out the super chat? That's fine. Just 2 seconds. Thank you, Vicky, very much for your £10 super chat. Really appreciate it. She sends me a super chat on her birthday, guys. Can you believe it?
Already done.
Chene support again. Thank you very much. And to celebrate the last part ever of Lucha's special.
Yeah.
Thank you very, very much. Really support your channel, support Vicky, and I hope you've had an awesome birthday. Thank you very, very much.
I guess it depends on how this part goes. If we're gonna
No,
do
Luke.
part 3.
Luke, if I'm spending my birthday listening to you, it is the final episode ever.
Hey, that's not nice.
Hey, she complimented you last night. She said congratulations. Congratulations for not getting timed out.
I did.
Yeah, that's true. Thank you for that.
You're welcome. Don't get used to it though.
Oh, well.
Okay, Anthony, up to you, man.
So I heard you say before, I came in because you said a couple of things, and I was just wondering if I could just clarify a couple of things with you. One of the things that you said was that that gas has got weight, and that scuba tanks demonstrate it by putting a gas in a scuba tank and then weighing the gas in the tank. You can minus off the scuba tank's weight, and then you can calculate the weight, right?
Yeah,
in
that
that tank,
sense.
while there's gas in there. Well, that was what you said, and that was what I wanted to challenge, because I want you to tell me what the behavior of the molecules is doing inside that tank. One of 2 positions is true. Maybe you could tell me which one is true. Is it A, the gas molecules are all bouncing down towards the bottom, and that's what's pressing on the scales? Or is it B, they're moving freely in all directions, bouncing in all directions off all sides of the container inside the scuba tank, and there's no particular directionality to it whatsoever? Which is the position?
Well, if it's completely full with gas, then they wouldn't really. It would be so compressed that they would have no ability to move. So yeah, they'd be pressing downwards.
Okay, so
by
let's just go with 1 or maybe 1 or 2 molecules, whichever you prefer. Let's not go with full, because that gives the impression that you're treating gases as liquids, and we know they don't behave like that. So let's deal with just 1 or maybe 2 molecules. Tell me what's happening with the molecules. Are the 2 molecules bouncing freely in all directions randomly and every now and again hitting each other? Or are they bouncing up and down and only bouncing up and down?
Well, probably, if it was, I'd imagine that they'd be have a bias downward.
Okay, which leads to the next question. They don't, but this leads to the next question. Have you heard, you've heard of the gas laws, right? You've heard of like Gay-Lussac's gas law, Avogadro's gas law. You've heard of the gas laws generally. Have you heard of the dual expansion of gas law?
The dual expansion? No.
Yeah, it's actually the free expansion of gas. Just remember that.
It's also known as the free expansion of gas. It describes the behavior of gases as moving randomly in all directions, bouncing randomly off all the walls of the container. So the gas inside the scuba tank isn't going up and down. It's moving in randomly in all directions, whether that's full, half full, 2 molecules. They're moving around in all directions, bouncing off the containers of the walls, which means that when you put them on a scale, they're only measuring the ones that are bouncing off the insides of the container in the downward direction, because that's all scales can do. But if you were able to put those scales on the sides or the top, they would still measure an increase that you would call weight. But in actual fact, is the increase in pressure of the molecules bouncing against the walls of the container, applying the dual expansion of gas law. Now, the fact that gas law exists debunks the notion that there's a directionality of gas. Because if there was a directionality of gas, the dual expansion of gas law would not exist, and we would have a directionality of gas law in accordance with gravity. But we don't have that. We only have the free expansion of gas as per the dual expansion of gas law. So my question to you is, given that you think gas has weight, and given the definition of weight in physics is weight equals mass times the acceleration due to gravity, then given that the free expansion of gas law applies and we don't have a directionality of gas, how is it possible that gas can have weight when the only thing that we can agree on is that gas does have mass, but there is no acceleration due to gravity, and even if there was, it doesn't affect gases? So it can't, by definition, satisfy the definition for weight, because there is no acceleration to gravity, and even if there was, it doesn't affect gases. So that would mean that you've got W equals M times 0. And what happens when you multiply something by 0?
You get 0.
There you go. So by definition, applying your rules, gas cannot and does not have weight by definition or by applied mathematics.
But it does. It is affected by gravity.
Should I play it again?
Which gas law describes? Which gas law describes this behavior?
I can ask.
None of them do.
No further questions, Your Honor.
I'm going to play this again for you, Luch. Just listen to the words again, okay?
And in this What Is video, we're going to investigate the state of matter called a gas. Gases are materials that have no definite volume. And
gases have no definite volume. What does that tell you? First of all, Luch?
But gases have mass.
Gases have no definite volume. What do you need to have mass?
Hang on, let's address that. Gases do have mass. We agreed on that before. You don't have any acceleration due to gravity, right? Gravity is not a force. And even if it was, gas molecules are not affected by it. So you can't satisfy, by mathematical application, you can't satisfy the definition for weight.
Exactly. Because it's going to consist on what size container you got and how much of that substance you're putting in there. But that's why I say it's volumetric weight. It's not gas weight.
Oh, because
Flatzoid, I think the pennies dropped.
Also, hello, sleeping warrior. How's it going?
It's going good, sir. I'm really enjoying this hangout. This is beautiful.
It's funny.
I've seen you on like a few debates as well.
Okay.
So, yeah.
Did you only ever watch it from the perspective of? Did you only ever watch it from the perspective of an anti-flat earther?
Well, yeah.
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 You watched it from
this would be why. This is why you're struggling with the gas pressure argument, because if gas molecules have weight, then you need to come up with the formula for it. And we know what weight is defined as in physics. And we know that it needs to have an acceleration due to gravity to accelerate the mass. Well, we know that it doesn't, gravity, even if it was a force, we know that it doesn't affect these gas molecules. And we know that there's no gas law that describes this behavior.
But like we agreed that gas has mass and gravity exerts a force on all objects with mass.
No.
So then you would have gas law. then you would have a gas law that would describe this fiction that you're describing, where there's a downwards directionality of gas. What would be the gas law, please? If you don't have one, just say, because we do have one that says it's freely moving in all directions.
Probably F equals ma.
That's not gas law.
No, that's
you need a gas law.
not gas law.
You need a gas
it's
law to
gravity.
describe. Well, that's not even gravity, is it? That's a formula. And it's a formula
That's
for the acceleration
acceleration.
of mass using a force. And it's only a calculation. It's not actually a force. But I know you people like to substitute mathematics instead of experiments, hence why you would cite that. But F equals ma is only Newton's second law of motion, but you'll ignore Newton's first law of motion. For an object at rest, a
To
force
remain
is
in
necessary.
motion unless acted upon by an outside force.
Correct. So you haven't got a force, right? And even if you did have a force, it doesn't affect gas molecules. So therefore, because you haven't got an acceleration due to gravity, and you haven't got a gas law that describes this downwards directionality that you insist that we have, gas cannot have weight. It does not have weight.
What's your... Okay, so one more time. Simplify the problem that you have with gas having weight.
You haven't got an acceleration caused by gravity to cause the mass to accelerate. No gas law, no mathematical application makes it work. You need a gas law to support you need a gas law to describe the downwards directionality, right? And you haven't got one. We have. It says it expands freely in all directions. No downwards directionality. So you need a gas law in the first instance. You need to apply the formula for weight, which is W equals mg. You need to apply that to gas molecules, knowing that they move freely in all directions and therefore don't have a downwards directionality. And if you can't apply that mathematical formula, it cannot have weight. That's the problem. I can't make it any simpler because I'm trying to translate it into a language that you understand. But because it's cross-wiring your understanding, you're confused. That's the problem.
Well, we can say it easy again. I'm going to play this again and just listen to the words again.
What
Luke.
about-
Remember, we're not
what
saying
about-
this.
It's kind of PV equals nRT.
The ideal gas law. You do know that goes literally throws away your gravity argument. But just quickly listen to the words again, Luch. Okay.
No specific shape.
Your whole idea of, Mark has no answer. I do have an answer. Spheres kept there by gravity.
Third, gases can flow from one area to another. Although the direction of flow is not directly affected by gravity.
Spheres kept there by gravity.
Although the direction of flow is not directly affected by gravity.
Gravity.
Although the direction of flow is not directly affected by gravity.
So if the Earth had a container, as you claimed, you made a claim there that the Earth has a container over it. What ought to happen, according to the second laws of thermodynamics, is that the air should equalize to become the same pressure, like in an aeroplane or like in any other container.
Molecules in a gas collide with one another and move more quickly or more slowly based on factors like temperature and pressure.
It would not have a pressure gradient going up from high pressure at the bottom to low pressure at the top.
Good times for all, exactly, to bother here if you prefer. What we have is a bucket of ice water, okay? So, and that hose is coming out right here, and it runs up to this pressure reading gauge right here, which, as you can see, is right at about 3. And this one,
Going up a mountain, the air becomes thinner.
Everybody knows that it's colder up in the mountains than it is down below, and the difference can be quite substantial. Now, to understand why this change in temperature happens, we need to understand a little bit about gases.
In order to study the relationship between pressure and temperature, we will heat up a gas which is enclosed in a tight container. While we are heating the gas in the container using a burner, we can see that with the increase in temperature, the pressure of the gas also increases. And when we cool the enclosed gas, we can observe an obvious decrease in its pressure.
Now, when gases are compressed, they heat up. And when gases expand, they cool down. When the gas is compressed, it's going into high pressure and getting hot. And when it's being expanded, it's going into low pressure and getting cold. So the gas starts out at a certain temperature, and as it goes up to low pressure, it's being expanded and getting colder.
It becomes less pressurized. People have to take oxygen up Everest.
It's 2 cylinders. It contains all the regulators, the delivery mechanism, and the face mask.
You are absolutely wrong. And you've just shown that by claiming that there is a container around the Earth.
Let's just take a gas in some volume, V.
I love this one, by the way.
And over here is going to be
Vacuum.
Vacuum of equal volume. And we're going to remove the barrier. You know what's going to happen spontaneously, right? The gas is going to fill the available volume.
Based on this quickly, Luch, what would happen if you stuck the vacuum on top of that gas container? Would it still fill the available volume up?
Yeah, I'd imagine so.
Joules free expansion of gas.
Pull it down?
So it'll still be Joules free expansion of gas. That's exactly what Anthony's telling you. Let's get to there again.
Okay, maybe I need to reword the statement a bit then.
Down.
Just like she said, the gravity is not it's not directly influenced by gravity.
Oh, yes, great. So you can see then gravity can't do anything to gas then.
But it can, because buoyancy is also part of the gravity equation.
Total non sequitur. Buoyancy has got nothing to do with gas behavior and gravity pulling it out as a force.
Buoyancy causes gas to go higher, therefore gain.
No, it doesn't. Gas moves in all directions. Gas is unbonded. Buoyancy does absolutely sweet bugger all to gas, mate. PJ Cruikshank, thank you very much for a £10 super chat. Another Chennai support. Luch has a very lovely blue.
You got £10 because of me.
Thank you very much, man. I really appreciate the Chennai support. You rock, man. You're ready. Thank you very much.
Thank you.
But you get what we're saying, Luch. It's like when Sleeping Warrior was on here now. He's trying to explain to you, due to gas behavior, gravity has no effect on gas. And if you can't show us any gas law that shows gravity doing anything, then, well, you don't really have a foot to stand to say gravity is pulling gas down, because it totally defies physics and gas behavior.
Temperature differences can also influence gravity's flow.
Temperature influences gravity?
Gas flow. Temperature can also influence gases flow as well.
No, temperature influences the speed at which the gas is moving. So it will manipulate it into how much pressure it's got, but that's not gravity.
Warmer gas is less dense, right?
Yeah, but it cools down as it expands.
And it rises, and cooler gas, well, that's the opposite.
Because we live in a dynamic system. Exactly. That's why we have pressure gradients. But the issue here is you guys are claiming gas does not require containment, because you're claiming gas can be affected by gravity, even though that goes against gas law.
The cause of this is, definitely temperature induced, right?
So not gravity then.
As well. And
so not gravity then.
And gravity has an indirect influence on it.
Gravity can't do anything. It's not a force.
Yeah, now we need a definition for gravity.
It's indirectly influenced by gravity, but the main cause is temperature.
Do you know what free expansion
What's the influence of gravity?
No.
What's the influence of gravity?
No, but before we get there, Anthony, I just want to ask him because he doesn't know what free expansion is. It's simple. No energy change, just simply entropy. In other words, if it's expanding outwards, it's not taking any energy. It's just expanding.
Yeah, free expansion just means non-directional, all directions.
So it's part of the thermodynamics then?
Yeah, Joule's free expansion.
It's part of the
gas. Gas laws.
I guess. So gas, is it vacuum related? I guess it would be.
Vacuum related. Right. Can
Gas
we have a definition for what you...
expands into a vacuum, right?
Yeah, pressure into a low pressure. Yeah.
Or area of no resistance.
Yeah. Apart from in your special pleadings example where you believe that the Earth exists in a vacuum but doesn't press into it, with the exception of that special pleadings fallacy, gas always presses into low pressure.
Well, actually, we say low pressure system.
Yeah, which is what wind is. We see that all the time.
We don't say vacuum. We say a low pressure system.
Yeah, we see that with wind all the time. High pressure.
Yeah, it's Bernoulli's it dropped. It's Bernoulli's principle. Do you understand, Lou? Do you understand how Bernoulli's principle works?
Who?
Bernoulli's principle.
Bernoulli's principle. No.
It's the way an aeroplane wing works to fly. It causes a low pressure to be situated above and a high pressure, so it actually pulls the plane upwards. It's simply entropy. That's Bernoulli's principle, mate. It's simply showing the direction of entropy, high pressure to low pressure. That's why a plane's wing is designed a certain way, so it's able to give it more lift. Do you understand?
I guess in a laboratory setting, where it under controlled conditions, free expansion can happen on Earth.
In any condition. If you go and let's take a balloon with gas in. Can anybody on the panel tell me what will happen to a balloon if I had to pop it in any environment?
That's a difficult one.
The gas will expand into the space.
So expansion.
But
yeah,
Earth is not a vacuum.
No, Earth's definitely not a vacuum. Nature abhors a vacuum. There's no such thing as a natural vacuum, only a low pressure system. But you guys are ignoring the low pressure system is in the same dynamic system we live. So it's still in the contained system. It's like taking a swimming pool, filling it up with water, then taking another container, sticking it inside the pool, and claiming there is no swimming pool.
Isn't like free expansion the thing where gas expands into a vacuum or an area with no resistance without, doing
it just means expanding freely. No, it just means expanding freely in all directions. No, the key word here is freely in all directions. You see, that's why gas pressure literally debunks the notion that gravity can pull gas down, just by gas being a gas.
Yeah. It's by gas behavior, yeah.
Mm-hmm. Is it a bit hard to take in now?
A vacuum provides the ideal conditions for free expansion.
You don't need a vacuum for free expansion. As I explained, you can take a balloon and I can pop it here at ground level. It's still going to do exactly the same as if I had to pop it on top of a mountain. It'll still expand freely into the surrounding system.
Definition: free expansion. Free expansion typically refers to the expansion of a gas into a vacuum or an area of significantly lower pressure where the expanding gas does not encounter any substantial resistance or external pressure.
So if I had to take a balloon, you've seen when a high altitude balloon pops. Is there any resistance for that gas to expand?
When a high altitude balloon pops, there's less, but there's still some resistance.
There's no resistance. That's why it's called free expansion of gas.
Yeah, that's why it typically has to be under controlled conditions.
Can you find me anywhere, even in a vacuum, where there is no gas already in the vacuum?
If you take the gas out of a place, then that would be a space with no gas in it. If you manually take every gas out,
it's impossible. Exactly, Jeff.
Exactly.
No,
you don't get. Are you claiming you can get zero pressure?
Zero. Yeah.
Where? Prove that.
Like if you manually did it in like a laboratory setting.
No, you can't.
You could.
Impossible, dude. Impossible.
There's no such thing as negative pressure. You can't get zero. There's always 0.000.1. If there's one little molecule, it's still pressure. You can never get no pressure.
Okay. I'll admit defeat. I'll admit I was wrong now.
That is becoming ridiculous.
But based on that now, Lou, you would agree then that the globe has a huge issue when they're claiming gravity as containment for gas.
The technology we have could create an extremely low pressure, but not like the elimination of all particles.
Exactly.
So it would still be.
No, but that's not my point. My point is based on this information, you would agree the globe rhetoric that claiming gas is held down by gravity has very, very big issues.
Gas being held down by gravity. Can we continue?
I'll take that as a concession.
Okay, it's got to be a concession.
Okay, let's move on.
Well, it's just because I don't have an answer right away. I'll think of one.
Later, gotta go.
Later, Jeff. Bless you, man.
Cheers, Jeff. Thanks for coming, man. I appreciate you.
Yep.
Bye, Jeff.
Cheers, man. Okay, so analogy for better understanding. A coffee in a cup analogy. Imagine you have a cup of coffee representing the earth, so containment, okay? And the steam represents the atmosphere. The steam rises and appears to disperse, but a majority of it stays close to the cup. Gravity acts as the heat. No, that's false, though. Steam will always disperse. I thought I heard a pung. Even, as the coffee cools down, the steam will no longer be there. It will all disperse. It won't keep steam there indefinitely. So that's a bit of a weird analogy. And gravity acts as the heat of the coffee, providing energy that keeps the water molecules, in this case, the atmosphere, close. Without the cup, Earth's gravity, the steam atmosphere would indeed disperse. like I said, so gravity is not a force, so it can't pull gas down. Gravity has no direct direction on the direct attributes to the direction of gas. Gas always moves in all directions, and based on the Joule's expansion, free expansion of gas,
Yeah,
it
it is a
implies
weird
that gravity
one.
being, yeah.
It is complicated. I'll admit that it can get very complex.
It's actually very simple.
Like even I don't
The globe and
fully
the globe
understand it.
No, the globe rhetoric makes it complex. It's not really complex. It's very simple. The gas has to go somewhere. And it will go somewhere, whether you believe it or not, because there is no force to stop the gas from going up. Gravity is not a
we can have a look at this then. Newtonian gravity,
which was superseded by Einsteinian gravity 109 years ago.
Look at that.
That means
That's
it
the next
replaced Newtonian gravity. Do you know the difference between? Do you understand the difference between Newtonian gravity and Einsteinian gravity?
One's relativity and one's very basic.
No, do you know the mechanics between the difference in mechanics between the two?
One depicts it as a force and one depicts it not as a force.
So if the one's a mechanical force and the other one's not a force at all, how can they be saying the same thing?
Well, it's just that it acts like a force.
So
since gravity does all of the things that a force basically does, it can be considered as a force.
So then you guys are saying Newtonian
but it's not a force.
F equals ma is false.
But acts completely like a force. So it can be considered
but let's
a
put it this way. You would agree that Newton's laws of motion, second law of motion, F equals ma. Would you agree that's true? That holds true?
Yeah. It hasn't been debunked,
So so Einstein, you're telling me now gives the same thing, so it acts like a force. So in other words, you're telling me thanks to Einstein, you don't require force for a mass to accelerate.
It acts. It basically does the exact same thing as a force. So.
But it's not a force.
But it's not a force, yeah.
So then F equals ma is debunked then.
But F equals ma
because you don't need a force then
debunked.
to accelerate masses. Is that what you're saying?
It's never really been debunked. So.
It's very
Not
simple.
fully.
The statement is you require a force for a mass to accelerate. If you're now claiming you do not require a force for a mass to accelerate, that debunks F equals ma. You either have to state F equals ma holds true or it's debunked. You can't have it both ways. Which one is it?
Well, the first simplicity. It makes things simple to use F equals ma.
So you can calculate it as a force. Does that make it a force?
If you can calculate it as one, I don't know. Let's see.
You're not getting it. If I have to push a car, I am pushing with the force to accelerate the car.
Yeah.
Do you agree with that?
You are.
Yeah.
Now, if I'm not pushing the car and the car just seems to accelerate without even having a force attributed, would that be debunking the notion that I need to push the car?
Maybe the car's on a hill.
Oh, so it's an unbalanced force. Like relative density disequilibrium.
Well, relative density doesn't really
have a vector.
Yes, it does. Relative density sigma does have a vector. You know if it's going up or down. Definitely.
No.
Yes.
Density is just the amount of stuff that's compact.
Into
Yeah,
volume.
and if there's exactly. Say PJ.
I'm just saying. I'm just agreeing. Stuff, amount of stuff packed into a volume. Yeah.
Hmm?
Yeah.
So you would agree
that
if you have
doesn't
more
mean-
mass packed into a volume, it has more potential energy.
So, do you agree that mass attracts mass then?
No, there's no such thing as mass attracting mass, just unbalanced forces.
Because if you send, density is the amount of, well, I guess mass stuff compact or something into it.
Mm-hmm.
It doesn't have a direction.
Okay, let's put it this way. If I had to take a pillowcase and I started shoving feathers into it, you'd agree the more feathers I'm shoving into that pillow, the heavier it's going to get.
Yeah, it would have to be a lot, but yes, it would get heavier.
So more substance, there's more stuff in the pillowcase to make it heavier.
That's more, yeah.
Okay. And because it's heavier, would it require more force for me to pick that pillowcase up now that it's full of feathers, where before I fold it up, it would take less force to pick it up?
It would require more force, yes, it would.
Great. So you would agree I used the force to accelerate that pillow when I picked it up.
Yeah.
Your gravity is saying there is no force. The pillow just picks it up on its own.
No.
Yes.
You should read the next thing. That's about Newtonium and Einsteinium gravity.
Yeah, I know what we're going to get there, but like I'm trying to explain to you, that's exactly what it is. The one is explaining that acceleration with no force there. It's only an apparent force. The one explains it as an actual force. Okay? What did I want to say now? I wanted to say something very specific now. I can't even remember what I say. But oh yeah. Do you understand, based on general relativity, if something is falling, it's not falling. The Earth is rising up to meet it.
Yeah, that's one way to look at it.
So if I'm picking up my phone and I let it go, we're rising up to meet it. The phone's not falling. It's just staying there where it is.
Basic observation, you could say either one is true. So, yeah.
No. But you understand what I'm saying? So in other words, the phone's staying where it is. We are rising up to meet the phone because there's no force acting on this phone. The net force is zero. It's staying where it is. We have a force rising up to meet that phone.
I guess so. Is that what it's
So
saying?
is the phone accelerating or are we accelerating?
We would be accelerating upward to meet the phone.
And where's the force that caused us to accelerate up if there's no force? How are we accelerating towards that phone if we don't have any force attributed to accelerating us?
That's not, no, because it can't be, because it's like the bending and warping of space-time. General relativity. That's what general relativity
It's literally just a mathematical construct.
Yep.
In a fourth dimension that doesn't even exist.
So if you place, it's like a big mattress, a big soft mattress. If you were to place something on it, it would bend inward towards it. And if
is that
you place
mattress
another
physical?
thing, it would roll down.
Is that mattress physical, Lou?
Yeah.
And when you stick a heavy weight on there and it puts a divot, is that physically imparting a force to create that divot?
Yeah, it would be, right?
And is that then causing an unbalanced force for something else to be able to move towards that divot?
Yeah.
Okay, now, is that a physical force moving?
Physical force.
Is there a physical force moving that, let's say, a small mass into the divot? Or is it just simply the ground beneath it falling away?
Well, it would have to have some kind of force acting on it.
No, it's an unbalanced force.
Because
There is no force.
If you just put it there and there's no force, it won't move, right?
But you see what I'm saying? So you either have to say, yes, F equals ma is true or it's false, because you either require force for something to accelerate or you don't require force for something to accelerate. If you're using the mattress analogy, you don't require a force for acceleration, do you?
No, the big ball is the thing that's creating.
No, the big ball's not doing any force on that small ball. It's not even interacting with it.
But it's the reason why that small ball moves towards it.
There's a reason why it's moving towards it. Why is that? Because it has an unbalanced force. It has what you call impulse. It's moving because it's moving.
Moving because it's moving.
Relativity.
Hey, Sob, good to see you, man. Thank you for coming. So think about it. It's very simple. In matter of fact, general relativity is literally trying to explain relative density disequilibrium, but in a mathematical base in Narnia. Do you get that?
So, well, it wouldn't be. Well, since general relativity says no force, it wouldn't even be an unbalanced force, would it?
Google that.
Because general relativity says there's no force at all, right?
But yet you see acceleration.
But in Newtonian mechanics, forces are considered balanced.
Yeah, exactly. So it's two different mechanics. They can't be the same. They literally are two opposite sides of the spectrum. And that's why we're trying to explain to you guys. When you want to say you can use it as a force, even though it's not a force, is literally wrong and a contradiction.
If the object they act upon, unbalanced forces result in acceleration according to Newton's second law of motion. That would be F equals ma.
Did you get what he's saying?
Say space-time curves. Let's see. Appears as from that perspective, their movement is simply a consequence of following the straightest possible path.
But you get what we're trying to say, Luch?
I think I see the confusion.
What's the confusion?
Maybe for I think I'll have to look into it a bit more.
Okay.
Don't come back for another episode.
Yeah. Since I'm unprepared, I'm gonna let you have the victory for now.
So for now.
for now.
Okay. Are we going to move on to the next one then?
Yes. Let's do it.
Which one is the next one? Earth rotation?
No, that would be the
atmospheric
more.
movement.
That would be up. That would be the Newtonium and
It's still Newtonian now.
It's up.
Science?
It's
You
up
want to do
a bit
science?
more. It's up a bit more, but yeah, let's do that one. That one's a small one.
Okay. Science involves the study of cause and effect relationship as a fundamental aspect of understanding the natural world. I agree with that.
Yeah, absolutely.
However,
Perfect statement. Perfect
true statement.
Yeah.
Heard another ping, sleeping warrior. I see he's having issues coming in. Devices
no.
with-
1, 2, 3. I think you can have 6 in, can't you? Well, we've only got 4, so it's still
No,
good.
his device not connected. Oh, there we go. Add stage. I think he's
Oh,
having issues
hello.
with his.
It's coming in.
Just before we move on, I just want to pick you up on one little thing you said before. You said density itself is not direct. There's no direction to density, right? Because it's a measure of how much stuff there is in something. That's what you said before, correct?
Yeah, that's correct.
Right. That totally agree with that. Density on its own has no direction. It is a measure of how much stuff is in stuff. That is what density is. Density equals mass per unit volume. However,
Yes, that's correct.
what you guys always negate to mention is the second part of the sentence, which I always have to add on to you, and then you just go silent, which is, but when you have two densities that are competing for the same space, there will be a displacement. That's what you always miss off. So whilst I agree with you, density is just a measure. When you have two densities next to each other competing for the same space, there will always be an acceleration, unless the densities are equal.
Do you think you would be able to
Welcome
answer
to
the
relative
three-body
density.
problem there? Or do you think you'll
So-
be able to answer the three-body problem there?
When you have two densities that are next to each other,
Competing for the same
What?
space.
that are competing for the same space.
Yeah, so they're in the same container.
Okay. What would happen?
An acceleration.
Think about it.
You can demonstrate an acceleration. In other words, there is a directionality in a vector. There is a directionality with a magnitude, demonstrable scientifically, repeatable, verifiable, complies with scientific method. When you get two relative densities competing for the same space, provided they are not of equal density, there will be an acceleration. Scientifically, empirically validatable, repeatable. All school children should get told this, but do not.
So they need to have different densities.
Provided they've got two different densities competing for the same space, there will be an acceleration. Only where the
So-
densities are identical will there be none. And that was what I demonstrated with the egg. There was no difference in the
Equilibrium.
density, in the average density of the egg. Yeah, equilibrium.
So that's what I'm
when-
trying to say. I think they don't really understand that the underlying argument is relative density disequilibrium is real physical world demonstration showing
write that
general
down.
relativity, trying to explain it in mathematical terms.
I'll write that down. So when you have two densities that are competing for the same space, would you be able to
Provided they are not of
demonstrate
equal density.
providing they have different densities?
Yeah, and there will be an acceleration. And it's scientifically
So could you-
verifiable. It's scientifically validated.
You would be able to demonstrate an acceleration then.
Yeah. Yeah. I did that for you with the egg test. That was why the egg was stuck in its position. The egg was sat stationary within its position, right? It was competing with the container. They were competing with the water, the salt water, inside that container. And they're both competing for the same space. But because they were both of equal density, the egg was of the same equal density of the medium, there was no acceleration. Yet when I changed the density of the medium, an acceleration was caused.
Yeah.
Wait a
Now,
minute.
you guys
Is
say
that
that,
when-
you need a force
is that
for it,
the-
applying Newton's first law of motion.
Oh no. Would that be the I think I get the confusion with this one. I might be able to answer this one.
Okay.
Really?
Let's hear it.
Well, then,
It's
what's your
when you-
confusion?
Wait for it.
It's when you had it's a video you did with the salt water and the egg, right?
Yeah.
The egg experiment.
Yeah. So you adding the salt to the water changed the buoyancy. So
No, because
yes,
density is a
so
measure
now-
of how much
so you
stuff there
changed
is
the
in an
buoyant
object.
force by adding the
Now,
salt to the
buoyant
water,
force
which
relies
made the
on
egg move.
gravity to be a force, but we know gravity is not a force. Hang on,
Which
we know gravity is not a
acts like
force. So by adding salt, it can't have affected. Yeah, no, it doesn't act like a force. It acts like an acceleration. It's not an actual acceleration. It just appears to be accelerating. But my egg wasn't appearing to be accelerating. It was actually
But you would
accelerating.
agree.
So there has to be a force acting on the egg.
But you'd agree that if gravity was a force, the buoyancy equation would have made the egg move.
No, buoyancy equations don't make accelerations. You need forces to make accelerations. Equations don't cause acceleration. So no, the buoyancy equation would not have caused the acceleration. No, that's wrong.
You've changed the buoyancy there. You've changed the buoyancy of the water by adding salt to it.
No.
Therefore,
No,
the
I've
egg
changed the
moved.
density of the water because density is a measure of how much substance there is inside something, which is the salt inside the liquid in this case.
Sure, you've changed the density, but you've also changed the buoyant force as well.
What buoyant force?
No, there's no such thing as
And
buoyant
that's
force
why
because
the egg
gravity is not a force in the
moved
first
upwards.
place. No.
The egg
So,
moves
right,
upwards,
gravity's not a force. Gravity's not a force, and it can't pull on the medium to create a buoyant thrust upwards. It needs to be a force to do that. Now, even if you think of it as a force, we're seeing actual acceleration. Gravity is currently defined by Einsteinian gravitation as an apparent acceleration, not an actual acceleration. We're seeing an actual acceleration, so there needs to be a force. We can identify the force. We can
The
cause
buoyant
it.
force.
We scientifically validate why the egg moved.
The
Not
buoyant
buoyant force. That
right?
needs gravity to be a force to pull on the medium.
Yeah.
There's no such thing as buoyant force. Gravity doesn't exist as a
There's
force.
such a thing as buoyant force there.
You first have look. It's this way.
No, there's not.
Luch. You first
needs
have to
gravity to be a force.
You first have to understand that to have a buoyant force, you have to have gravity as a force. Since gravity is not a force, you wouldn't be able to have the buoyant force.
For simplicity, you can say it's a force.
But it doesn't make it a
But
force
it
because you
isn't
say
a
it's a
force.
force.
You can pretend that my car's a Ferrari, but it doesn't make it a Ferrari.
For gravity, it's different.
So you've got a special pleadings fallacy then. This is logically fallacious. You have a
You can,
special
like,
pleadings fallacy to make
if
your
you
gravitational model work.
Hold on, look at the go back to my Discord message. I have a thing about it. We can look at that one.
Okay, let's quickly go look. You want to
I
go
think it's more up than
gravitation.
where we were right now.
The force of the concept. Why the force concept persists.
Yeah, it's around there. Yeah, that
You want, no, but is that the one you want, or practical
it's,
utility, or general relativity and gravity?
yeah, it's the Newtonium and Einsteinium and why the force concept persists. That's what I want. Yeah.
Okay, so we're going to start with general relativity and gravity there.
Okay.
Or do you want it almost you read from the beginning?
Yeah, you can read from the Newtonium one.
Okay.
Yeah, do that one.
By the way, everything we've just said literally answers everything you just wrote in here. But okay. Isaac Newton's law of universal gravitation, formulated in the 17th century, describes gravity as a force that attracts two bodies towards each other. Just like we just said, it's been falsified. General relativity states it's not a force, so therefore you cannot claim it to be a force. This force is directly proportional to the product of their masses. And someone's, hey Z, what's up, man? Good to see you. And then the mass is inversely proportional to square of the distance between their centers. You sound very much like FTFE here, mate. Newtonian formulation of gravity as a force provides remarkably accurate predictions for most everyday purposes, including planetary motions, tides, and projectile trajectories. Nonsense, to tell you the truth, though. Gravity is not a force. Practical utility for engineering, basic astronomy, and other fields. Treating gravity as a force is sufficient for practical designs. You do know that they just have an average acceleration. That's what they do. Luch? They put in their calculations.
No.
Yeah, it's based for an average acceleration.
Flatzoid, may I have a few moments with Lou, if you please?
If he says it's cool, yeah.
Yeah, sure.
It's
why
good to
not?
see you, man.
Hi, Lou.
How's it going?
Howdy. Pleasure to meet you.
Yeah, pleasant to meet you too.
Yeah, so just a few questions for you. Straightforward questions, no guile. I'm not here to try to insult or ad hom or clown. I always enjoy these conversations, and I think he's doing well. I think you're doing well, Lou. You appear to be sincere, and I always appreciate that. But I wanted to ask you about centrifugal force. Are you familiar with centrifugal force?
That would be the would that be no? What is it?
Okay. Have you ever been on let's say a ride at the carnival called the Gravitron, or have you ever been to a child's park with a like a merry-go-round? And as you're spinning around, there's a force that's pulling you out, which would basically be tangential to the direction of motion.
Yes, when you that's I know what it is. Yeah.
Okay.
Go on.
Right. Okay. So can we both agree that on a spinning globe, there would be a centrifugal force? For instance, if I'm at the equator and there's apparently about 1,000 miles an hour velocity, there'd be a centrifugal force associated with that. Can we both agree with that?
It would be incredibly slight, but yes, I suppose
All right.
I would.
Well, okay. So, and then can we both agree that would be in your model gravity that offsets this centrifugal force? Would that be correct also?
That
if the Earth is spinning, and then by nature we know that when things spin, there's a propensity for centrifugal force, then under your model, we can obviously assume that gravity is what's offsetting that centrifugal force. Would that be a correct statement to you?
Well, the
centripetal
would no what would feel would be the acceleration. So, and that would be around, I think, 0.34, right?
Well, yeah, I know you're trying to get into the maths, but I'm just trying to keep it basic and logical and sequential here, because under the model that you're basically defending, the idea is that gravity is what's needed to overcome the centrifugal force, and that's what holds us from just flying off into space. Can you see that connection?
We probably wouldn't need gravity to keep us from flying off the Earth.
Okay, so what would you propose that keeps us? Because you're defending a model that claims that we are spinning. If I'm correct here, so if we're spinning, there must be, if we're spinning, there would necessarily need to be a force to keep us stuck to the ball. Is that not correct?
Unless you're spinning very slowly.
Okay, so would you consider 1,000 miles an hour, which is faster than the speed of sound, slowly?
At the 1,000 miles per hour.
Oh, I want you to think about it. So there's an Earth. Yeah.
Sorry, I just want to say, think of it this way. Like a Bugatti Veyron at full speed is about, I think, 180 meters a second, where the Earth is said to be at like 480 meters a second at the equator.
Right. Let's think about it. We're talking about roughly a 24,000 mile circumference and a 24-hour day. So with very simple math under the model, that equals roughly 1,000 miles an hour to complete the 24,000 mile circumference in a day.
It would be 1,030.
Correct.
Miles
Yeah. So 1,030 miles an hour spinning around an axis would necessarily imply centrifugal force. So the model claims that gravity is what offsets this centrifugal force. This is the model that you're defending. This isn't my model or my contention. This is the globe model. So is it fair to concede simply that the force of gravity that you're espousing is then offsetting this centrifugal force? Is that correct?
It's a sphere with 360 degrees. It takes a day, so divide that by 24 hours in a day, and we'd get 15 degrees per hour, right?
Right.
So that's how fast we are rotating. We're rotating at 15 degrees per hour. Also, it would be a
right
a
15 degrees, right? So we know there. Here's my point, Lil, is that if indeed the force of gravity is what's equalizing out the centrifugal force at the equator, my question is to you, what is the centrifugal force at the pole, at the North Pole?
It would be zero, wouldn't it?
It would be zero. So how is the same gravity that's overcoming the centrifugal force at the equator, moving at 1,000 miles tangential to the center? How could that same gravity be acting uniformly when there's zero centrifugal force at the pole compared to maximum centrifugal force at the equator?
Maximum centrifugal force at the equator would be about 0.3.
Okay. Well, it has to be relative to something. So that's not relative. So my point is this: if the gravity that is holding you to the spinning Earth at the equator is supposedly uniform based on the supposed tenets of gravity, how can that same gravity then also be not crushing you if you are at one of the poles where the centrifugal force is zero? It debunks the globe on its face, and if you think about it, you'll understand what I'm talking about.
It's 9.8 meters per second. That's the acceleration to gravity.
Right. That's what they're claiming. So if that 9.8 meters per second, which you're claiming is a force, if that force is enough to offset the centrifugal force at the equator, that same gravitational force would crush you at the pole.
No.
It debunks it.
No, it wouldn't crush you. That force is very weak. It's a very weak force.
It's only weak based on comparison to electromagnetic force. I would agree with you there. It's claimed to be weak because it's claimed to be a force. This is the point we're trying to make as you continue to beg the question and presuppose gravity.
But it's the weakest it's one of the weakest forces we have.
Right. That's the claim. How could you prove it's a force? See, you've continued to beg the question of gravity through the conversation as you're trying to prove it.
He's actually
the,
double speaking because he knows it's not a force, but he's pretending that it's a force, and he's pretending that it will accelerate matter, but we know it doesn't.
He's doing
It's not
exactly.
a force.
He's doing exactly what George Musa did. He's doing
can
exactly what George
definitely
Musa did.
hold on. We can definitely see that mass attracts mass with the
No.
Cavendish experiment.
Oh
No.
wow.
No.
Well, we can observe it. So yeah.
Well,
that was
I've
true,
seen the Cavendish
if
experiment.
that
Okay.
was true, it would
What's
debunk
that?
Einstein, and Einstein's theory would never have even existed because there would be no need for it to exist because the Cavendish experiment would demonstrate that Einstein was wrong.
The Cavendish experiment is basically the curvature of space-time, according to Einstein. We can see
No.
that one mass curves the space-time, drawing the other mass into it, which is
Really?
how relativity would describe it. But F equals ma, or Newton would describe it as just one mass pulling on the other.
That's not how it would be described in Einsteinian. Let me correct you. Bear with me, gents. If Einstein's interpretation was to be transposed into the Cavendish experiment, what it would be perceived as from an observer from millions and millions and millions of miles away would be that the balls would appear to be attracted towards each other. But that wouldn't be an actual acceleration. It would be an apparent acceleration caused by the lensing of the medium between the observer and the balls warping because of mass.
Do you want me to? Do you want
how
me
it
to
would be
use?
perceived as an acceleration from one observer of an object not actually accelerating.
Do you want me to use Einstein from now on then?
No,
You'd
I
be
just
better
wanted to
off
acknowledge
sticking.
that only the observer from millions of miles away would observe an apparent acceleration when there was no actual acceleration to be observed. He would only perceive that acceleration, that apparent acceleration, because the medium between him and the object that he's looking at, the Cavendish balls, would be moving, squashing, like affected by space-time curving by the mass. That's all. It's only from his perspective would that be the case. So no, a Cavendish experiment is claimed to be actual acceleration. That's not comparable with Einstein. You've got it wrong, I'm afraid.
Which is neither scientific nor an experiment, like Sovereign said. Yes, I mean.
Yep. And I mean, like I say, we can demonstrate where you can do Cavendish and nothing happens, or it goes the opposite way.
No, you can't.
Yes, we can.
How's that?
How's that? Because it's not even an experiment to begin with. What's the independent variable for the Cavendish, dude?
I have that on the. Hold on, let me find that on the Discord thing. Let's see.
Hang on, we need a definition for. We need him to understand what it's defined as first before you get him to identify
before we move there,
What is the independent variable? Tell us what an independent variable is.
The Cavendish experiment and the Foucault pendulum. I have them both in there. So here we go. Can you hear me?
Yeah.
Yeah.
Okay. So, well, which one do you want? The IV or the DV?
IV.
IV.
But first
Okay.
go and first tell us what the IV is, though. Define what an IV is.
It's the controlled variable, right?
No.
It's the one.
No.
It's changed or controlled. That's what it is.
It's the manipulated variable.
Yeah.
That's you manipulate it. You control or you change something, and that manipulates the outcome. Right?
No, that's not precise enough. You need to do it again with more precision. Apply the scientific definition, not your understanding or the colloquial. The actual definition. What is it?
The definition of an IV in a scientific.
The scientific one.
Okay. Let's say. independent variable. Scientific experiment. Let's see. Experiment. Let's say.
Lou, I hope they pay you by the hour, buddy.
Okay, let's see. In a scientific experiment, the independent variable is the factor or condition that is intentionally manipulated or varied by the researcher to observe its effect on another variable, known as the dependent variable. The independent
Perfect.
variable is...
Do me a favor. Do me a favor. Read that to me again, but actually pay attention to what it says.
Yeah.
Because you read it, but I don't think you understood what was being said. So read it again and understand what's being said.
In a scientific experiment, the independent variable is the factor or condition that is intentionally manipulated or varied by the researcher to observe its effects on another variable, known as the dependent variable.
Perfect. Now let's try and apply this in the Cavendish experiment. Would you like to lead?
What?
Or it doesn't matter how we get there, but you can pick. There's a gotcha. You're screwed because you've just read the definition correctly. Now, when we apply that definition in the Cavendish experiment, what is the variable that was manipulated by the researcher? What did he vary?
I'll read what the independent variable was in the Cavendish experiment. Let's see if I can find it again. Let's find it. The IV of the Cavendish and focal pendant. Oh, there it is. The Cavendish, the IV, the independent variable. Let's see. That's the fact on the dependent variable. Yes, that's correct. Okay. In the Cavendish experiment, the IV independent variable can be considered the distance between the large and small lead balls. Cavendish varied.
Perfect. So, whoa, stop. So it wasn't gravity then, was it? It was the distance between the balls that caused the effect. Distance, right? Is distance, is that a force or is it a measure of something?
Well, according to, the distance and according to the gravity, it would be m2 and the distance between them and stuff that would affect the gravity.
So not gravity then, distance.
Distance has an impact, yes, on gravity.
Distance by definition was your cause. You told it me.
Yeah. He manipulated the distance between them.
Therefore, gravity was not varied or manipulated by the researcher.
But according to what gravity is, gravity has a large impact on, how far away something is.
Well, we know what gravity is. It is defined as the effect of the curvature of space-time caused by the uneven distribution of mass. That, by definition, is what gravity is. So when you've just juxtaposed gravity as your understanding of it, you've just converted it back into a force as per Newton, correct? Well, that's not what gravity is anymore. It's been superseded 100 years ago.
It can be considered a force, though.
So my car can be a Ferrari then?
With the...
Just because you think of it as one.
Why?
Can my dog be a donkey?
If it chooses to be, warrior, nowadays, if it chooses to be, it can be.
No, but he doesn't identify as a donkey. But from your perspective, you think that something can be a force when it's not a force. It's defined as an effect of the curvature of space-time. That's not an apparent force. It's an apparent acceleration, but it's not actual acceleration.
Simplicity
it's caused by the lensing of the medium.
Newton's force-based gravity is mathematically simpler and more accessible for most people to understand and apply. It requires less background in mathematics and physics to use effectively in many contexts.
But mathematics.
I think this is a good question that Sov's asking. What happens if you only have one weight?
Acceleration.
If you only have one mass in and nothing else, nothing would happen. You wouldn't be able to observe anything happening. Not really.
Yeah, but we don't observe the acceleration due to mass anyway. Because if we did have an acceleration due to mass, helium balloons would have to go down.
Helium balloons are buoyant force related, so.
No,
the
gravity is not a
buoyancy.
force. You keep applying a force. Yeah, buoyancy is not a force. It needs gravity to be pulling on the medium to make the balloon go up. Well, we know that gravity is not pulling on the medium because we went through how gas doesn't have a directionality to it. It moves freely in all directions. So there's no downwards directionality to give buoyant force to a helium balloon. You're wrong.
But now we should ask, what's the dependent variable there?
So the question is, how does the buoyant force work if gravity is not a force? Huh?
There's no buoyant force, mate.
We know what causes buoyant force. I demonstrated it with the egg. What you call buoyant force is what is actually changing the density of the object or the medium relative to the other thing. It's called relative density, but you call it buoyant force, which is based on a non-force. But you can think of it as a force. It's ridiculous. It's absurd.
Yeah, but think of it now. We're going off topic a bit, just like TV says. Now, what is the dV, Lou?
The dV, let's say, that would be a bit lower. Let's see. Okay, why? Oh, a bit lower. There we go. The dV, the dependent variable on the Cavendish experiment. It's the thing being tested and measured. Let's say, in the Cavendish experiment, the dV, the dependent variable, is the amount of torsional twist of the wire or the angle of rotation of the torsion bar, which is a measure of the gravitational force between the small and large balls. This twist or rotation occurs as a result of the gravitational attraction between the small balls on the torsion bar and the larger balls placed nearby.
Did you just make that up?
No.
That bit's not in there. There is no gravitational attraction between the balls. There is none. I know you think there is, but there is none.
But there's though.
If there was, gravity would need to be a force, but we know it's not a force. We know it's an apparent acceleration caused by the curving of space-time. And it has to be viewed from many, many millions of miles away. That's not what we're observing with the Cavendish non-experiment. What we're observing is an actual acceleration, the cause of which you can't prove. You insist that it's gravitational acceleration, but it isn't because we know it's not a force. So it can't be that. You must be wrong by deduction.
Mm-hmm.
Well, also,
why I want to know how the Cavendish experiment works when gravity is not a force.
Well, here's a problem too, Lou. Here's a problem too. You have to have controls. You have to have controls. And that's why I asked what happened when one weight was used. You said probably nothing. Shut up! Probably nothing. So was it ever tried using one weight to see if there was any movement with just one weight?
That's what the Cavendish experiment
is. Went in with already reification of mass attracting mass. They already went in with a reification of that, so they didn't test it with any controls at all.
And I just want to say, Dal's in chat. Hey, Dal, good to see you. It's very simple. How does matter cause its own motion? An unbalanced force. Just like you have a bowling ball on a hill. You let go of that bowling ball, it will have its own motion due to an unbalanced force.
So yes, that would be
Think about this, Lou.
the force equals the gravitational constant mass 1 of mass 1 times mass 2 over the radius squared between them. The radius of the distance between them squared.
But you're not listening to what he's saying specifically, Lou.
You're saying that since gravity is not a force, it shouldn't work?
No, we're saying that because gravity is not a force, it isn't responsible for what you claim is the actual acceleration between masses. Well, gravity, even by current science, is not an actual acceleration. It's an apparent acceleration. So therefore, by deduction, you can rule out gravity being a force as the cause of the acceleration that you insist is caused by gravity, because it isn't a force. Deduction, it's called.
So check this out. If you had a bathtub, Lou.
So
if you had a bathtub,
why do the balls move towards each other then?
Lou,
Who
So
cares?
Lou,
It's not our claim.
Lou, Sovereign was talking. Sovereign's talking.
What's it?
All right.
He
So
was talking. He was talking.
So
here's
why
the thing, Lou.
So
Here's
why
the thing.
do the balls move towards each other then?
Lou, you're doing it again. You're
Okay, I've
talking over
muted Lou
something.
just so he can listen. Go on, Self.
So I'm asking, if you had a tub, a bathtub, and you've got it full up to the brim with water, and you get into that tub, what forced the water to yield to your body and overflow? What forced that water? What was the force involved?
Still getting into the water.
Right.
What, like the water rises and spills out?
Right. What forced the water to yield to you?
I guess it would
He's
be
asking you to identify the force.
you adding more mass to it? I don't know.
Could it be something like displacement?
What is displacement?
Because two objects cannot occupy the same space at the same time, so one is going to yield to the other.
Yeah.
So then this in this case, you have your body and the water is the medium. So you displaced the medium and you forced the medium to yield to your body, correct?
I suppose so.
So is displacement a force?
Not buoyant. So not buoyant force then, right? It wasn't buoyant force.
It was displacement.
So why does water rise when you add more mass to it?
Because you're
he's talking about this displacement. He's taking up the space, so the water has to move out the way.
Right. It's everything's a big teeter-totter. Everything's a big seesaw. Everything is a big seesaw that wants to be level. It wants to be equal. Everything wants to be equal, but it can't. It's always in a state of disequilibrium, so it's constantly changing, right? So what happens when we displace the medium? It's either going to be this, okay? You're going to either be equal to the medium, or you're going to be heavier or lighter than the medium, okay? And if one thing is it's going to act in a manner to try to equalize. So if you're heavier than the medium that you displace, you're going to go down. If you're lighter than the guy on the other side of the teeter-totter, it's going to go up, right? Meanwhile, this medium and the object cannot occupy the same space at the same time. So therefore, displacement takes place. The medium is yielding due to what force? The force of displacement.
When you put an object in water, it pushes some of the water out the way.
Yep.
The water has to get somewhere.
So not buoyant force.
So the water level rises.
Yeah, so not buoyant force then? Can we get that conceded? Because
No,
you didn't concede it with what?
The
did
phenomenon where water rises when you add mass to it, or in a bathtub or something, it can be explained by the principle of buoyancy.
Yeah, but you can't have buoyancy. Whoa. Again, we've said this to you. You can't have the buoyancy if gravity is not a force.
So, which is why I say, like, that you need to like look up why. You need to look up if gravity is not a force, why does buoyancy include it as a force?
Because they're making it as if
It's not our
gravity
claim.
was a force.
Yeah, it's not our claim. It doesn't matter what he thinks. What he thinks that we need to explain is irrelevant. It isn't our claim. It's your claim that mass attracts mass, and we can demonstrate that that's not true. We don't have to explain anything beyond that. If you want to know why you think that mass attracts mass, go right ahead. Make a hypothesis. Publish a paper. You might win a Nobel Prize. Apparently, you win Nobel Prizes dead easy in this topic. So go and tell us how you do it.
So yeah. So you want? Okay, I'll try and explain why buoyancy includes gravity as a force when it's not a force, I guess.
Yeah, that's the problem. We know what causes the acceleration that you call buoyant force. We demonstrate it. It is repeatable. It is scientifically validatable. They should teach it to children in school. We know what's doing it. It's not buoyant force.
But it's still valid.
It isn't. It's called bullshit. It's like saying, I don't have a Ferrari. But if you think I've got a Ferrari, then I'm rich. But I don't actually have a Ferrari, so I'm not rich. But teaching kids that I am rich is just lying. We know what the cause of what you call buoyant force is, and it's not gravity. You don't have to like it.
Let's see. In classical physics, buoyancy is described as a force that results when an object is immersed in a fluid, liquid, or gas. This buoyant force arises because the pressure at the bottom of the object is greater than the pressure at the top, leading to a net upward force. This difference in pressure is due to the weight of the fluid, which is directly related to gravity. Thus, in a Newtonian framework, gravity is essential for the existence of buoyancy.
Yeah, there you go. Gravity is essential for the existence of buoyancy. So what happens if gravity is not a force? It's essential for your belief, right? And it doesn't exist. What does that do to your belief?
Well, if gravity doesn't exist, then we'd have to find out another way that it could happen.
Well, maybe if you varied the density of the medium, like I did, you might be able to cause the buoyant force. Just saying.
Okay, fair enough.
Yeah, but
Let's
it debunks your notion.
Let's quickly. Yeah, it's very simple, Luch. It's not a force, so you can't have your buoyant force. You're just literally contradicting yourself. Yeah. And then I'm just going to tell Del, you literally have to calibrate an accelerometer, man. You can calibrate it to have a reading when it falls, just like you can calibrate it to have no reading when it falls. Just stop spamming your religious beliefs by our channel, please.
I'm sorry.
No, I'm talking about Dal, Beyond the Curve.
Yeah,
He still believes
okay.
if you drop an accelerometer, it shows no acceleration. Where the moron doesn't understand, it's calibrated to do that.
Yeah.
He says, does it accelerate
to
towards the
opposite.
ground? He dropped the lighter and he picked it up and dropped it. It didn't just appear there and drop itself.
Yeah.
I noticed
Poor
Del
guy.
never mentions why it is the egg went up when a variation in density was caused. You know, like by manipulating that density, Del, an acceleration was caused. You never seem to mention that. You always seem to talk away from that. Wonder why that might be.
Because he's dishonest. Notice how he lies to everyone and says none of us want to actually converse about this. But I think I've tried to talk to him about it 2 or 3 times already, and then I get blocked while I'm trying to talk, or he gets triggered and swears me off and then kicks me off.
Yeah.
But I don't want to talk about it, no. But I go to his channel. That's why I've just ignored the bloke. The guy's got nothing. He's literally just clutching at straws.
I wonder what made him come in tonight. He hasn't been in for a little while, has he?
I wonder. Well, if you, if you dropped, like, was he saying that the accelerometer was dropped?
If you drop, let's say I got my phone.
Uh-huh.
It's got accelerometer. Okay, you can calibrate it to when it falls, it shows 0G. Now you can calibrate it to do the opposite. When it's sitting still, it can show 0G, and when I drop it, it shows 1G. It's calibration. It's literally software.
So you think the accelerometer is a lie?
No, there's acceleration. He's claiming because if I drop an accelerometer on my phone, it shows 0G, therefore it's not accelerating. It's an apparent acceleration. We are rising up to meet the phone. In other words, he's a globetard.
Yeah.
In a pizza.
He's a sideways globetard.
Yeah, he's a globetard with a pizza.
Anyway, this guy's using Dell as a distraction to pull away from the point. Yeah, so let's go back to it, right? Your own citation said that gravity is fundamental for the existence of buoyant force, or words to that effect.
That's correct. Yeah,
we've demonstrated by deduction gravity cannot be a force. It is an apparent acceleration from an observer millions of miles away, as per current science.
Okay,
that is the current position. Whether you agree with it or not is irrelevant. That is the current position. But if you want to pretend that that's a force, that's fine. But if it doesn't actually exist, then your notion of buoyant force has gone bye-bye. See you later.
But we have general relativity now, so it's fine.
No. It's not fine because general relativity is not an acceleration. It is an apparent acceleration, and this doesn't cause buoyant force that you call. It debunks your notion that gravity is a force. It debunks your notion that Cavendish was a mass-attracting mass force. It debunks your notion that the sky can have a downwards acceleration that you call weight. It debunks all of your heliocentric nonsense, because if gravity is not a force, even if you can think of it as a force, it's not pulling the sky down for us to be able to breathe in a vacuum. It's fundamental to your religion, mate.
But Einstein said general relativity. So even if gravity is not a force, it would still work out.
No, it wouldn't. Again, from an observer many millions of miles away, he would perceive an apparent acceleration, not an actual acceleration. You guys are talking about actual accelerations. Einstein's doesn't comply with it at all. It doesn't explain it. It doesn't help you. It's a false equivalence. You don't understand.
Flatzoid.
Yeah.
Well, I guess I'm sorry for wasting time.
No, man, don't stress. This was an awesome show. And I think it was needed because a lot of people have the same misunderstanding like you do.
Yeah, that's what I was going to say, Lou, is those are questions that a lot of people have, a lot of conceptions that people have. And it's great that you come in, you have a semi bit of conviction to them, and we're able to discuss them, and you don't get all flapped out of shape. And this is good. This is for the listener, Lou, as well as you. The listener is getting information because they're going, oh, I thought exactly the same thing that Lou said, but wait a second. this other information contradicts it, and so it's opening up people's minds. You're helping with that, Lou.
Well, I guess I'll have to. Well, I'll have to thank Sleeping Warrior as well. Thank you, Sleeping Warrior.
I've got a query for you to ponder. Next time you come in, maybe you could give us an answer.
Okay.
You know how you say that the sky's got weight, air's got weight, right?
Yeah, the Earth, yeah.
Do you agree that when you remove the medium in a vacuum, do you agree that whatever's in the vacuum, let's just say you've got, I don't know, a football or something, not a football, something that doesn't stretch. Let's say, I don't know, a trophy. You put a trophy in there. When you remove the medium, do you agree that the trophy gets heavier? Or do you agree that the trophy gets lighter when you remove the medium? What happens?
If you put it in complete space, would it get lighter?
No, you get an object. Doesn't matter what. We'll call it, I don't know, something that's not stretchy. Like I said, football initially. That's a bad example. We'll go with a trophy because it's metal and it's solid and it doesn't stretch.
All right.
You put that in a vacuum chamber and then you remove all of the medium out of there. So you're just left with the object inside the chamber, but the air is no longer in there.
Okay. Yeah.
What happens to the weight that is being measured on the scale? Does the weight get heavier or does it get lighter?
I'd imagine lighter, right?
Well, you would say that buoyant force is acting on the weight, so that if you removed the weight, if you removed the medium, there'd be no buoyant force. Correct?
Or
no?
Yeah.
But you also say that the air is pressing down on objects, giving it weight. The air's got weight, so that would mean that there's weight pushing down on the object. So if you remove that, then it would get lighter. Correct?
Well, it's gravity's the main cause as to why things have weight.
Let's focus on this. We've got an object in a vacuum, and we remove the air. What happens to the scales that's measuring the weight of the object? Do the scales increase or do they decrease with the value? And why? Because this is a paradox for you. You're screwed with this one because on the one hand, you'll say that, well, there's a downward force caused by the air, which is pressing on the scales. So when you remove the air, the scales will get lighter. So that's what you would say. But in real world, when we remove the air, the object on the scales increases its weight, which is contrary to your claim that air's got weight.
So if you place a trophy or something solid in a vacuum chamber, right? Yeah. And so would it get lighter? Is it the question?
Do you want to quickly check?
No.
Sovereign has a video
in real
up that
world,
can tell you.
In real world, it actually gets heavier, right? But if your version of the world is true and air has weight because there's a downwards directionality to it, if you remove that downwards directionality to the air, then it must get lighter. But in real world, it gets heavier in a vacuum. Therefore, another way of debunking the notion that air has weight, gas has weight, it doesn't have weight. Because if it did, objects in a vacuum would get lighter because you're removing that downwards force. But they get heavier, directly debunking the notion that there's a weight to the air.
Exactly.
Would it even change in weight at all?
Yeah, check. So I'm going to quickly play a piece of a video for you.
And part of it in the middle, he's got an in-video advertisement, but I can move through that when he gets there. So no worries.
Just go to where he's measuring it.
The mass of an object is a measure of its matter.
What?
And the weight of an object is, the force exerted on it, right?
Well,
according to our heliocentric thing, gravity would be the cause of weight, right?
No. You do know weight and gravity are two different things, though.
Gravity causes things to have weight.
No.
No, it doesn't. Gravity causes things to appear to acceleration from an observer many millions of miles away. That's its definition today. You're applying the definition from 100 years ago that you were taught in high school. That position is no longer the current position. It's changed.
And that would be relativity.
No, that's still gravity, but your understanding of it is what you were taught in school, which is not the current position in science. Again, the definition for gravity in science today is an apparent acceleration of an object where none is actually happening, and it's observed from an observer many distance miles away, and it's the medium that's causing the apparent acceleration. It's like refraction. You know, when you see things moving in the horizon, the shimmering, they're not actually moving, are they? It's the medium between you and it that's moving that gives you the impression that that's moving up and down. But it's not actually moving up and down. That's a direct equivalence to what gravity is. It's the appearance of an object accelerating when it's not actually accelerating, caused by the medium that you're looking through. Lensing, it's like lensing. Hence where the phrase comes from.
It's more than...
No, it's not. That's what it is. No, that's what it is. It's not more than something. That's what it is.
I should say it, what's the better word? Encompasses, maybe? Yeah, gravity...
No, that's wrong.
Encompasses more than just apparent acceleration.
Sorry, guys,
it doesn't encompass more than an apparent
acceleration. We can't go on
acceleration.
all night, though. Is it okay if someone just plays that quickly? Yeah, he's very wrong.
Yeah.
Is it okay if someone plays that part where he measures to show you the difference in weight?
Go ahead.
Here we go.
I'll tell you how you weigh more in a vacuum. And I'd like to thank Morning Brew for sponsoring this video. I'll tell you a little bit
Morning Brew.
So I have a plastic bottle with air in it. Right now, if I weigh this on the scale, I'm actually only weighing the plastic bottle because I have air inside the bottle and outside the bottle. But if I remove the air from around it, then I'm weighing a different thing. I'm actually weighing the plastic bottle itself, and I'm weighing the air inside of it. So let me show you what I mean. I'm going to put this empty bottle on a scale in the vacuum chamber, and you'll see that when I remove the air from around it, it suddenly starts to get heavier.
Ooh, why is that?
So right now it weighs 11.434 grams. Let's turn on the vacuum. And it immediately starts
It's getting heavy. Check there. You can see it's getting heavier.
Which is why when you lift a bucket of
we're using grams. This is a measure of mass, but when you use it,
But Lou, that says then the gas is not pushing up from on top like a column of air.
No, it's not pushing down on top. That means that it's directly debunking the claim that the atmosphere is pushing down on you with weight.
When you lift a bucket of bricks in water, it's way easier.
Stop. Deal with the evidence. The evidence demonstrates that when the downwards acceleration that you call weight of the air was removed, oddly, the mass got heavier. But if your claim was true that the sky has got weight, the air has got weight, if you remove that weight, that downwards pressing, it must get lighter. But it didn't. It directly debunks the claim that atmosphere has got weight.
Yep. Exactly.
No, he does a solid. He does a solid object in here too. Yeah.
But Sleeping Warrior. TB says I must just correct you quickly. Space-time warping is a concept in fourth dimension, not science. I think we all agree with that.
Oh yeah.
I was correcting him with what he understands gravity. Apologies, you are correct. Space-time warping is conceptual. It's not actual. Although actually, LIGO is claimed to prove that space-time does bend, but let's not go there.
But yeah, guys, I think that was a good show. Sorry, I got to end it. I mean, I also got to go sleep before I get up just now.
Well, I enjoyed it. Well, thank you.
It was good.
I don't know how,
but I think
how did you enjoy it? How did you enjoy getting battered?
Well,
I think Anthony, maybe we should organize a stream where we all come back and actually chat about the subject, because I think we can do easily 4 hours on just this alone.
Yeah, you could. You could.
Easy, yeah.
Yeah.
But I think we had a great discussion.
Yeah.
Like I said, you are actually just a flat earther. You're just in denial, mate.
Yeah, that's it. It's just the cog dish you need to get over, Luch. You'll be all right.
Unfortunately, no.
It's
Well,
claustrophobic. It's claustrophobic in the closet, dude. Come out.
How would I even be able to tell if I was a flat earther?
You
Easy.
are.
Our previous stream, remember you said it's flat and I put up on screen?
Hey, that was a joke.
That's a proclamation. That's it.
I
You can't go
even
back
said
to Bitoon or FTFE now and just
I even said it
they won't
after.
have you back. They won't have you back, dude. Not after admitting you're flat earther.
I said it after. I said it was a joke after.
A joke, yeah. We're just pulling your socks, man.
Alright.
But yeah, well, I think I enjoyed the show tonight, guys.
Yeah, well, thank you for coming in, Sleeping Warrior.
Oh, definitely.
Maybe
I'd
we
like you
could
to
have a
come back.
discussion, just two of us.
I'd like you to come back at some point with an explanation for why that object, that bottle, got increased its mass when the guy removed the medium, which you said has got a downwards directionality to it, a weight. Why did it do the opposite of what you would expect? Come back with an actual answer for that, and we can discuss that, because it is directly debunking your claim that atmosphere, the air has got weight. I want you to come back and tell us why we're wrong.
So, why you want our explanation as to why it would get heavier?
Yeah,
No,
because
no.
your claim that gas has weight pushes down on things. This totally debunks that, because if gas was pushing down on it, it would be heavier than in a vacuum.
So
and it gets heavier in a vacuum because
there's no air, right?
Pushing down on it anymore?
No, there's no air pushing up on it anymore either.
A solid object.
Oh, but you said it was pushing down before.
There's air all around it, so.
Yeah, but so it's not pressing down then, is it? If it's being removed from all directions around it, you're literally debunking yourself. So not down then. So not down then.
Hold on, it would be pressing in all directions. So
not down then.
Down, up, all around, including down.
Displacement.
Not down then.
Not just down.
Displacement. So you're describing displacement.
In all directions evenly, wouldn't it? Apply the fuel expansion.
Yes, it would be in all directions evenly. It would be pressing in all directions.
Right. So you've just debunked, whether you realize it or not, you've just admitted that there is no downwards directionality to the sky. In other words, the sky does not have weight. Weight requires an acceleration due to gravity, and gravity is only in the downwards direction. That's where you get weight from. You've just admitted it's in all directions, so it's not in the down direction. It's in all directions evenly, not down.
Weight is mass times gravity.
Right. And gravity is only in the downwards direction, is it not?
Yeah.
Right. So if you remove the air, you're removing that downwards acceleration that's caused by gravity pressing on the bottle. You're removing that, aren't you? But in the real world, when we test it, it doesn't do what you say it would do.
The downward acceleration would be the center of Earth.
I know. So if we remove that downwards acceleration, the air, then what must happen to the weight of the object? It must decrease because you're removing the downwards from it, right?
Wait. I've got an idea how we can make it simpler for you, Lou. Have you ever played in a classroom with all your friends and everybody's packing on top of each other? And the more people getting on is getting heavier.
Uh-huh.
Mm-hmm. What happens when the people start getting off?
It gets lighter.
Yeah. There you go.
So the bottle got heavier, yet you were removing the weight from above it. You have no explanation.
But there was also air pushing below it as well.
What you're describing, Lou, is displacement. Okay, the weight is nothing more than a ratio. We quantify it into pounds, stones, kilograms, whatever, grams. We have a quantification, but it's nothing more than a ratio of the relative density of the object within the given medium. This is why obese people this is why obese people have to do physical therapy in a pool, okay? Because it gives them more neutral buoyancy. It reduces their weight. It's less of a struggle for them to be able to move. You understand? And so they are actually weighing less when they are in the water than they do when they're in the air. It's all just a ratio between the object and the medium that it's in.
Let's pick him up on what he just said. He just said that the bottle had air pressing on it from the underside as well. Did you not? Correct?
Yeah.
So then it's not being pressed on from the downwards direction, is it? It's being pressed on it in all directions, not down.
All directions.
There was no. I think. Okay, no. The main direction is down.
Oh
no! All directions. You said.
All directions.
Not down.
There is
all
air
directions
underneath it, which would make it.
Yeah, I know. I know. But the problem is, if there's a downwards directionality to the sky, if you say that the air's got weight, then it's only the downwards direction. But you've just admitted it's in all directions.
There wouldn't be a force pushing it in all directions.
So therefore, not down then. Therefore, there's no weight to air. Therefore, there's no weight to air if it's in all directions.
No columns of air.
We may need to do a part 3.
No columns of air.
Yeah. Yeah, you need to go away and think about that, and then come back to us with it. Come back to us with an explanation.
So,
Good boy.
What was the So, if you put a trophy in a vacuum chamber and take out all of the air, it would get heavier. And you say, why?
No. Let's be really clear. Your claim is that air has weight, so we can test it. We can put any inanimate object in a vacuum chamber. We can remove the air from it, and then we can see what the effect is. And if it's true that the air has weight, when you remove that air, that weight must also decrease because you're removing it, so it must get lighter. However, in real world, when we remove that medium, it gets heavier, and you have no explanation for that because it debunks your notion that the sky has weight.
Exactly. But yeah, we'll get back to this another time then. I really got to go sleep, guys.
If air has weight,
I really can't go on forever.
Okay,
So,
one
thank
last
you.
thing, just to clarify. The thing I'm looking into is if air has weight and you're putting an inanimate object inside in a vacuum chamber, it shouldn't be heavier.
It should be. You would say it's lighter. No, hang on. Because you say that the air is pressing down on the object because the air's got weight. So when you remove that, it should get lighter. But in actual real world, it gets heavier, and it directly debunks your claim that the sky's got weight. You need to work out why. If we're wrong, you need to work out why.
And you put an inanimate object in a vacuum chamber. Why does it get
heavier?
Why does
it get heavier?
Okay.
If the sky has weight, or if air has weight. Because that's what it actually does in real world. I know in your model, it's supposed to have weight and it's pushing down on us, giving us atmospheric pressure. But in real world, we can demonstrate that's not true.
All right, I'll look into why it gets heavier. Got it.
Good man.
Cool.
Lou, I put a link to the video in the chat, in the private chat for you if you want to check that out about weighing more or less in a vacuum. From the Action Lab. That's a good channel, man. They do some pretty cool experiments on there.
All right. I'll look into that.
Yeah. Well, I think it was great. Thank you guys for coming. I really appreciate you guys. It was an awesome show. But I will definitely organize for with the Sleeping Warrior again and everything, and we can have a nice conversation on this again. I think it'll be quite cool. But I'm definitely going to go sleep now, guys.
Yep. See you in part
and I just want to say, this won't be a part 3. This will just be a discussion on gravity, probably.
Yeah.
See you for the gravity discussion.
Yeah. So thanks all for coming. Really appreciate you all.
See you later.
Thank you for hitting the likes, sharing the show, and appreciate all the panel members as well, and everybody who sent super chats. You guys rock. Thank you for all the support. And Vicky, have an awesome birthday further, even though it's an hour and a half left. But yeah, it was awesome having you all here, and I'll see you Wednesday, because tomorrow night it's. Have you sent the link already, PJ, for your guys' show tomorrow night?
There's no link yet, but there will be a show tomorrow night. It's 7.
Awesome.
On his world history.
Yeah, so look out for that. It's going to be awesome. Cheerio. Many blessings, and may the pressure be